Hello and welcome to this online module of online course on optical communications. In today's module we will discuss passive WDM components. WDM stands for wavelength division multiplexing, and it is a technology that is used in order to increase the rate of signal transmission over the optical fibers, in which multiple channels are multiplexed together, each channel carrying data at its own rate. They are multiplexed together so as to increase the usage of the optical fiber, the efficiency of the usage of the optical fiber. In order to facilitate wavelength division multiplexing, it is necessary to combine different wavelengths to select a particular wavelength. It is also necessary to combine signals at different ports, and then it is also necessary to isolate certain wavelengths, isolate signals from reflecting back and damaging certain components. So, all these operations require us to come up with newer devices, optical devices, which can accomplish these objectives. And in this module we will first talk about two or three such components known as couplers, isolators and circulators. There are additional WDM components that we will take up in the next module. We will defer the discussion of active components or the WDM active components such as photodetectors, although photodetectors are not technically active, and then lasers and optical amplifiers for some other time. Okay. So, our goal is to understand some of the passive WDM components such as coupler, which is a basic element. We have already looked at couplers when we discussed coherent receivers. We also discuss isolators, and it is kind of an extension called as a circulator. So, let us begin by looking at a coupler. We have already seen coupler in action when we looked at the coherent detection, because for a homodyne detection of signal we realized that you actually had to have a coupler. So, wherein one of the signal was coming in from the transmitted signal, and then the other signal was the local oscillator signal, and then we obtained two outputs. We obtained ES plus ELO by root 2, and then on the other arm of the coupler we obtained ES minus ELO by root 2. So, we have seen that if you give these outputs to the photodetectors, then you will be able to obtain the signal, which is basically a interference term between ES and ELO. It is kind of the down conversion process that can be performed for the optical signals. So, couplers in combination with the photodetectors actually perform the operation of the down conversion, right. So, we have seen this device as the front end of a coherent receiver. This coupler is a front end of a coherent receiver, and coupler, for our understanding, actually enabled us to combine two signals. Now, how exactly does a coupler do that? It turns out that what it employs is a principle. Suppose you consider a waveguide. Okay, it is certain signal is passing through this waveguide. This signal has a propagation constant beta. Okay. And then you consider one more waveguide, and in here let us say another signal is passing through. So, let us call this one as beta 1 and let us call this as beta 2 as the two propagation constants. It turns out that when you bring these waveguides closer together, then what happens is that for the combined waveguide system, that is, if you actually bring them in such a way that you fuse the two cores like this and then diffuse them again, diffuse in the sense that you simply separate them again. In this region, in the intermediate region where the waveguides have combined into a single waveguide, the propagation constant is neither beta 1 nor beta 2. The propagation constant will be a combination of beta 1 and beta 2. How exactly this combination occurs, what is the resultant value for the overall beta, is determined by what is called as the coupled mode theory. Coupled mode theory tells us that when you bring two waveguides carrying optical signals together, then there is a coupling between the two optical waveguides, which changes the overall propagation constant. Of course, it is not just the propagation constant which changes, what will also change is the amount of the power that goes out of these two ports. Traditionally, these are labeled as the input ports. So, let us call them as the input port carrying electric field E1 corresponding to an optical signal. This is port 2 carrying electric field E2 corresponding to another optical wave. The output ports are labeled as E3 and E4, which again represent the electric fields for the output optical waves. Okay. These E3 and E4 are actually related by a certain matrix. Okay. So, this matrix is called as a scattering matrix, and this is the kind of a matrix that you might have been familiar when you have studied microwave theory. Okay. So, it is kind of the same concept here. So, for that reason this is sometimes called as a directional coupler. Okay. So, this is called as a directional coupler because there is a certain direction to its input to output. Of course, the coupler is also reciprocal. Okay. It is reciprocal because you can turn around the input and output. You can make this coupler work in both ways. So, it is like a passive resistor. A resistor is essentially a bilateral or a reciprocal device. You can, there is no fixed terminals for the resistor to be put in inside a circuit. So, coming back to the matrix relationship for the electric field at the output and the electric field at the input, this is the relationship. I hope this E1 and E2 are visible at the end. Anyway, we will write down them slightly better here. So, you can see that the output ports are linearly related to the input electric fields. Okay. If you define the output electric fields, combine them into a certain vector, then you have a column vector E3 and E4. The matrix is represented by the capital letter S, and which will be a 2 by 2 matrix, and then the input can be given as an input vector which is given by E1 and E2. Okay. Now you have a matrix relationship which says that output vector is equal to S times input vector. Now, to actually obtain what is called as a lossless coupler, a lossless coupler would simply mean that the total power or the total energy from the input ports is preserved at the output ports. Nothing is lost in the coupler itself. So, the condition is that the total energy, as we know, is proportional to energy or intensity is proportional to magnitude of the electric field square. So, the total electric field in the input port is the sum of E1 and E2. Therefore, and since we are assuming E1 and E2 are to be independent of each other, the input energy, total input energy is given by taking what is called as the EI vector, multiplying it with EI vector. This Hermitian is simply designation for a matrix A. You can transpose the matrix and then take the complex conjugate of the elements. So, this is shorthand notation for Hermitian in my notation. Okay. So, this would be the total input energy. This has to be equal to the total output energy. Okay. So, this has to be the total equal to the total output energy, but I already know what is the relationship between output electric field and the input electric fields, right. So, output optical electric field and input optical electric field are related by the coupler matrix S or the scattering matrix S. So, taking the transpose of this equation implies that E0 transpose will be EI transpose times S transpose. Okay. And then taking the complex conjugate of that would give you complex conjugate on both sides. This transpose complex conjugate is what I am calling as Hermitian. Okay. So, I will essentially get for this E0 Hermitian to E0 as EI Hermitian S Hermitian S EI Hermitian EI itself. So, clearly if I want to equate the left hand side to the right hand side, this term which is S Hermitian S or S dagger S must be equal to an identity matrix. Since this is a 2 cross 2 matrix each of them, the transpose and the conjugate will also give you a 2 cross 2 matrix. Multiplying that with another 2 cross 2 matrix will give you an identity which is a 2 cross 2 identity matrix. What is a 2 cross 2 identity matrix? 1, 0, 0 and 1, correct. So, this must be equal to the transpose term. You can show that this transpose turns out to be S11 complex conjugate, S21 complex conjugate, S12 complex conjugate and S22 complex conjugate. This is the S Hermitian part. Multiply this one by S will give you S11, S12, S21, S22, and individually equating the terms will give you, individually if you equate these 4 terms, reduce the left hand side into a 2 by 2 matrix and then equate the terms to the right hand side, you will get actually you will get 4 equations. So, you get S11 magnitude square plus S21 magnitude square is equal to 1, S12 magnitude square plus S22 magnitude square is equal to 1. There are two additional 0 equations which are S11 complex conjugate, S12 plus S21 complex conjugate, S22 is equal to 0. You have the final equation S12 complex conjugate, S11 plus S22 complex conjugate, S21 is equal to 0. Remember, I said that this coupler is a reciprocal device, which means that if I interchange the inputs and the outputs, my coupler matrix relation should not be, the power relation should not be varied, right. So, I can interchange what I call as input into output. So, which means that my cross elements must be equal. So, S11 must be equal to S22, let us call this as equal to B, and S12 must be equal to S21, which I will call this as A. Okay. So, since these two are equal, you can substitute these B and A into above equations, and you will see that you get S11 mod square plus S21 mod square is equal to B square plus magnitude A square equal to 1. Please remember that this B and A are complex numbers. Okay. These are complex numbers. So, you can include, so this is the one equation, the other equation will be the same because S12 magnitude square is nothing but magnitude A square, S22 magnitude square is nothing but magnitude B square. What will happen to the right hand side equations? You get AB complex conjugate plus A complex conjugate B equal to 0. Okay. So, you get this other equation. These two equations determine the constraints on A and B. Okay. One such solution for these equations can be obtained if I consider B is equal to cos kappa L, where kappa is called as the coupling coefficient. Okay. Kappa is called as the coupling coefficient and L denotes the length of the coupling region. Okay. This is the length of the coupling region. So, this would be B equal to cos kappa L. So, clearly A must be then equal to sin kappa L, correct. So, that magnitude B square plus magnitude A square will be equal to 1. Okay. Now, this, if you substitute this into this second equation, so substituting B and A into this second equation will give you a relationship which can be written as, actually we have to also consider them to be complex numbers, right. So, we will multiply them by certain phase angle e to the power j phi b, e to the power j phi a to B and A, right. My magnitude square will remove this e power j phi b term and e power j phi a term, and therefore, they do not really change anything in the first equation, but for the second equation they will actually determine what should be the relationship between phi b and phi a. Remember, any complex number can be written in terms of its magnitude and phase, right. So, magnitude and its phase I can write it. So, putting this B and A into the second equation will give you an equation in terms of phi b and phi a, and I leave this as a small exercise for you to show that phi a minus phi b magnitude must be equal to pi by 2. Okay. So, you can easily show this one. So, phi a minus phi b is my magnitude must be equal to pi by 2 or any odd integer multiples of pi by 2. Okay. So, or it must be odd multiples of pi by 2. Okay. I will give you a hint as well where you can get this equation. You will essentially find this equation coming from this one. Okay. So, once you substitute for B and A into this equation, you will end up after simplification with this last equation, which is cos of phase difference must be equal to 0, and we know that cos phase difference goes to 0 when that phase difference term will be some odd multiple of pi by 2. So, we have relationship for phi a and phi b. It is common to consider phi b equal to 0 and therefore phi a is equal to pi by 2, right. This equation still satisfies my phase constraint because the phase difference between these two is equal to pi by 2. So, putting all these values back, you get the coupler matrix as cos kappa L j sin kappa L. You can say why j, because e to the power j phi a, e power j pi by 2 is nothing but j, right. So, you get j sin kappa L and cos kappa L. So, this is your coupler matrix. You can show that this coupler matrix satisfies the Hermitian property. Okay. Interestingly, now let us suppose that E2 is equal to 0, that is I am trying to use this coupler as a single input 2 output device. So, I will set E2 is equal to 0. If I do that, what will happen to my outputs? E3 will then be equal to cos kappa L times E1 and E4 will be equal to j sin kappa L times E1. You can see that whatever the signal that is going into the port 1 of the coupler is split into two parts. One part goes to the port 3 and the other part goes to port 4. What would be the power in each of these ports? The power, as you know, is proportional to magnitude of the electric field square. Therefore, the power fraction of the power in the first arm, that is in the third port, is cos square kappa L. Power in the second arm is sin square kappa L. Assuming again lossless coupling, the sum of these two should be equal to 1. But this cos square kappa L and sin square kappa L have an interesting behavior, right. So, as I change my coupling length L, okay, power in the third port initially is maximum, then goes to minimum, then goes to maximum in a periodic way, right. Whereas power in the fourth port, being proportional to sin square kappa L, will go in the opposite way. So, it goes like this. So, this is your port 4 output, whereas this one is your port 3 output. There is constant power exchange. You can now determine whatever value of L that you want, okay, in order to give a certain fraction of the output power. Suppose I want to send most of the power into third port, then I will choose my length to be equal to some L1. Okay. Let us also suppose that this power fraction should be about 95%, that is to say port 3 gathers 95% of the input power, whereas port 2 then must gather only 5% of the input power. What is the value of L1 required in order to do that? You can obtain this value of L1 by simply solving this equation. Cos square kappa L is equal to 0.95, that is the fraction of the power that goes into port 3. So, substitute, then you will get kappa L is equal to inverse cos of square root of 0.95. You can throw away the minus result for very obvious reason in this expression. So, given coupling coefficient kappa, you will be able to find out what should be the coupler length L. Okay. So, this is how a coupler behaves. So, for this scattering matrix that we have drawn, it actually connects the electric field at the input to the electric field at the output. You can actually find in literature, instead of talking about the amplitude in this way, the scattering matrix is written directly in terms of the power coupling ratios as well. For example, if the power coupling ratio is alpha, which means input comes in from port 1, alpha times input goes into the port 3. Of course, there is no amplification, therefore, alpha must be less than 1. Okay. In terms of the power ratio, power coupling ratio, the scattering matrix is usually written as square root of alpha j square root 1 minus alpha square root of 1 minus alpha j and then square root of alpha. Okay. Clearly, this matrix also satisfies the relationship. The advantage of writing this one is that you can easily obtain what would be the power ratio, right. So, alpha is the power ratio. Okay. Where in addition to being the front end of the coherent receiver, where else can we use couplers? Wherever you want to couple signals, you can use a coupler. Okay. Suppose I am constructing what is called as a Mach-Zehnder interferometer. Okay. A Mach-Zehnder interferometer takes input from two arms. Okay. So, this is input coming from port 1, this is input coming from port 2, and then it splits into two outputs. So, in port 3 and port 4. You can connect two waveguides here which will guide light, and then you create a small path length difference here of path delta L, and then you combine these two outputs. Okay. You can combine these two outputs in order at ports, say, so this is 3 and 4, let us call this as ports 5 and 6. So, this port at the output we can call it as 7 and 8. You can then show that output in 7 and 8, okay, when there is no input from port 2, will again go as cos square of delta, and this will go as sin square of delta, okay, where delta is proportional to the path length difference. Okay. So, you can show this, and in case you are interested you can take this as a simple exercise. What you will have to do is to relate E1, E2, E3 and E4 using this coupler matrix S. You can relate again using another coupler matrix S. For simplicity, assume that this is a 50 to 50 coupler, that is to say the power coupling ratio alpha is equal to 1 by 2. 50% of the power goes in one arm, 50% of the power goes in the other arm. Okay. So, this is how you can use couplers in order to construct a Mach-Zehnder interferometer. In fact, we will later see that this same Mach-Zehnder interferometer can be made use as a, or can be implemented as a wavelength filter. For certain wavelengths, which the phase difference will then be equal to 2 pi by lambda into delta L, right, that wavelength will be constructively interfered at one port and destructively interfered with the other port. So, you can actually create wavelength filters by using this Mach-Zehnder interferometer. The other area where couplers are widely used or used to be widely used is in connecting what is called as static wavelength cross connects. What is this cross connect? Suppose I have certain wavelengths, of course this is a kind of a simple thing that I am considering. Suppose I have signals coming in from two arms, okay. Then these were actually used for what is called as star coupling, that is for broadcast purposes. If I want to connect many outputs and then broadcast these results onto many outputs, then I could use many 3 dB couplers. This is one way. For example, I am considering a, let me just draw it correctly. So, I am considering 4 inputs here, these can be coupled, okay. So, there is one 3 dB coupler here. If I connect these two, I will get one more 3 dB coupler. I can then connect these two outputs, okay. I can connect these two outputs. So, this was known as a star coupler, okay. You can of course make this into multiple, in many ways you can implement this. In fact, you can implement this and then put some demultiplexers, okay, before you connect them, and then put some multiplexers after connecting in order to realize this so called wavelength cross connect, a subject that we are not going to touch for some time now. Okay. This is how we use couplers. Let us now quickly jump into what is called as a isolator. Isolators are very important in at least one major area. They are unidirectional devices, which means that if I put in an isolator, I have to specify the direction of the signal propagation. The signal propagates only in the direction that is mentioned in this arrow. For me, this would mean signal going from left to right. So, if I send in some signal from left, some output you can expect at the output, whereas if I send in input from this side, nothing will come out, okay. The input basically gets reflected or gets dissipated, okay. So, such a behavior is hallmark of an isolator. An extension of an isolator is what is called as a circulator. A circulator is a device which has a certain directional property as well. So, it is typically, we talk about a 3-port coupler. So, you have a 1, 2, 3 ports for this circulator. Any signal that goes to port 1 will be carried to port 2. However, there will not be any transmission from port 1 to port 3. So, we say that 1 to 3 port is isolated and port 1 to 2 is called as the throughput port or a through port, okay. Similarly, 2 to 3 is a through port, whereas 2 to 1 is an isolated port. So, you can see that signal can go from 1 to 2, but signal cannot go from 2 to 1. It will be routed instead from 2 to 3. Of course, when you send some signal from 3, then this will be routed to 1, okay. This is a 3-port coupler. You can also find a 4-port coupler in market that will again work in very similar ways, okay. How does an isolator work? Isolator turns out to be a non-reciprocal device. Why is it non-reciprocal? Because I cannot turn around the leads of an isolator, right. So, if these are the isolator leads, I have to use them in only one direction. In this way, they are equivalent of a semiconductor diode. I can't use a diode in without regard to its terminals. I have to know which one is the anode terminal of a diode and which is the cathode terminal of a diode. I have to put them in only one direction. If I put them in the other way round, then signal will not be passed. So, that is essentially an isolator. Okay. So, this isolator is built up on using a device called as a non-reciprocal. It uses inside a non-reciprocal device called as a Faraday rotator. Okay. Faraday rotator works on the principle of Faraday effect. If you apply a certain magnetic field, then you can actually change the polarization state of the input field. Okay. If the input field, for example, a Faraday rotator with a 45-degree rotation means that if I come in with a vertical polarization, okay, vertical polarization means that the tip of the electric field vector is vertical in a direction that is perpendicular to the direction of propagation. Okay. So, if I come in with such a vertically polarized light, then the Faraday rotator will rotate the polarization into a 45-degree angle. Okay. So, the output will be a 45-degree polarized light. What will happen if I come in with this in this direction? Suppose I start with an input which is vertically polarized, my Faraday rotator will again rotate it in the clockwise direction only. So, it will again rotate this one into this 45 degrees only. So, you see that in both ways it will rotate in the same direction. Okay. So, this is a Faraday rotator, this is used inside the isolator. Okay. How does an isolator look like? You assume that initially we are talking about what is called as a polarization dependent isolator. Okay. For a polarization dependent isolator, we assume that there is a vertical polarizer allowed. So, if I come in with horizontal and vertical polarizer, only the vertically polarized light will come out. After this vertical polarized light, I put a Faraday rotator of 45 degrees, so that the polarization becomes 45 degrees. Then what I do is I put a 45-degree polarizer. Okay. So, this is a 45-degree polarizer, which means that only 45-degree polarized light will be coming out of this particular polarizer. So, this is a vertical polarizer, this is a horizontal this is a Faraday rotator which rotates in a clockwise direction from 45 degrees. Now, suppose I want to look at what happens when I go backwards, right. So, I assume that initially I start out with a 45-degree polarized light at the right side. Okay. Now, when you pass through the 45-degree polarizer, no problem, this passes through the polarizer as it is, because these are in the same direction, right. Next, what happens is the Faraday rotator will rotate this one in the clockwise direction by 45 degrees, which means that the polarization state becomes horizontal now. Now, the horizontal polarizer is orthogonal to the vertical polarizer. So, this polarizer will not transmit anything. So, you do not get any transmission, right. So, the isolation basically depends on how good this polarizer is. If this polarizer is good enough in blocking the orthogonal component, then the isolation can be pretty high. Typical isolation is about 40 to 50 dB, and there is some insertion loss which is about 1 dB, 1 to 2 dB is the insertion loss when you go from one direction to another direction. We will stop now and consider few more components in the next module. Thank you very much.